Okie doke. We're now working on the second part of chapter 16, still talking about harmonic motion, and now we'll be talking about the various aspects of wave phenomenon and wave physics. And we're going to start out with problems regarding uniform circular motion and simple harmonic motion. So the first problem we're going to do is problem number 37. Problem number 37 states, what is the maximum velocity of a 85 kilogram person bouncing on a bathroom scale having a force constant of 1.5 times 10 to the 6th if the amplitude of bounce is 0.3 centimeters? And then what is the maximum energy stored in the spring? So just get an idea of what we're talking about here. We have a scale. We have a scale that's on a spring, or a set of springs, and an 85 kilogram person is up here, and this compresses 0.2 centimeters or 0.002 meters. And the question here is if this is moving like this, 0.2 of a centimeter, bouncing up and down with this person on it, and it has a constant, force constant of 1.5 times 10 to the 6th, what is the newtons per meter? What is the maximum velocity that this thing is moving at any particular time? As you know, when it reaches the top, it stops. When it reaches the bottom, it stops. In the middle, it has a maximum velocity. Now there's actually, in your book, there's a formula worked out for the Vmax, and that formula is equal to the square root of k over m times x, where x is the distance that the oscillation travels, k is the constant, and m is the mass. And so all we have to do is plug in the various components here. And since we always have to change the centimeters into meters because this is in newtons and this is in kilograms. And so we put 1.5 times 10 to the 6th here, and 85 kilograms here, and 0.002 meters here. And the answer is going to come out in meters per second. If you look, a newton is a kilogram meter per second. You divide that by kilograms and you get meter squared per second squared, it's kilogram meter squared per second squared. You divide by kilograms, you've got meter squared per second squared. Take the square root of that, and that's meters per second. Multiply it out, and it comes out in meters per second. And so if you do the math here, you get 0.266 meters per second, or 26.6 centimeters per second as the maximum velocity that this thing will travel. The formula for potential energy has not changed. It is still 1/2 kx squared, which is 1/2 times 1.5 times 10 to the 6th times 0.002 squared. You do the math here and you get 3.00 joules as the energy. 38. Number 38 states, it's down here, a novelty clock has a 0.01 kilogram mass object bouncing on a spring that has a force constant of 1.25 newtons per meter. What is the maximum velocity if the object bounces 3 centimeters above and below the equilibrium position? So you have basically a spring that has a little weight on it. The weight's 0.01 kilograms. The constant for this spring is 1.25 newtons per meter, and it's bouncing up and down like this, and at its midpoint, it has a maximum velocity. If the distance that it bounces is 3 centimeters or 0.0300 meters, then the Vmax, based on this same formula up here, is going to equal square root of k over m times x, which is equal to the square root of 1.25 over 0.01 times x, which is 0.03. And that's going to equal 0.035 meters per second as a maximum velocity. And the second part of this question is, what is the kinetic energy does this object have at its maximum speed? Well, it's the same formula you've known all along, 1/2 mv squared, where v is this v max here. So that's 1/2 times 0.01 times 0.335 squared, and that's going to equal 5.63 times 10 to the minus 4th times 10 to the minus 4th joules of energy at its maximum point. 39. Next question is, what is the position, at what position is the speed of a simple harmonic oscillator half of its maximum? That is, what is the value of the ratio of x to big X? What value of the ratio of little x to big X gives you a velocity that is plus or minus Vmax over 2, where x is the total amplitude. Now, this is a little more theoretical, but if we look at this, if we say that Vmax is equal to the square root of k over m times big X, okay, then V over Vmax is equal to the square root of big X squared minus little x squared over big X. And this comes from, if you look back in the book, they work a problem like this in the book. And that can be simplified. You can simplify that to square root, which is, if you square this, putting it under the square root, then this is going to equal 1 minus little x squared over big X squared. So 1/2, which is what this is for this problem, is going to equal square root of 1 minus little x squared over big X squared. And if you square both sides, you get 1/4 is equal to 1 minus little x squared over big X squared. And you shift that to, so you end up with moving this 1 over here, and that gives you negative little x over big X squared. So that those minuses go away, and you take the square root of this, and that's going to give you little x over big X, which is what you're looking for. And you simplify this, and it ends up with the square root of 3 over 2. And that's the answer, is the ratio of the little traverse to the big total amplitude is going to equal to this, the square root of 3 over 2. So it's not exactly 1/2. Number 40. Number 40 states that a ladybug sits on a 12 centimeters from the center of a Beatles music album, spinning at 33.33 revolutions per minute. The radius here is 12 centimeters or 0.12 meters. What is the maximum velocity of its shadow on the wall behind the turntable if the illumination is parallel to the record by parallel rays of the setting sun? So that what they're saying is you have a bug sitting out here going like this at the rate that it says, and light is coming in like this, and it's causing this bug to go like that. It's shadow. That's the way it'll go, back and forth. So what it's asking the question, what's the maximum velocity for that? First of all, if we calculate the angular velocity based on this revolutions per minute, 33.33 revolutions per minute is equal times 1 minute is equal to 60 seconds. That cancels these two guys. Times 2 pi radians is 1 rev. And if you do the math here, it's supposed to be 60. If you do the math here, you get 3.49 radians per second. So the angular velocity here is 3.49 radians per second. So that means that the maximum velocity would be the point where this is equal to the linear velocity, meaning it's going to equal r times omega, which is going to equal 0.12 times 3.49 radians per second. And you end up with 0.42 meters per second as the maximum linear velocity here. It's the point here where it occurs, and at that point it's equal to the linear velocity of this angular velocity. Okay, so that's number 40. Number 41. With number 41, we are talking about dampened harmonic motion, which is a harmonic motion that has some form of resistance or some form such as friction, which we will talk about in just a minute, or other means in which the motion itself is decreased with each. So you start out with a motion that looks this big, and at each subsequent point there's a loss in amplitude like that. And that's what's meant by dampened harmonic motion. So the question says, the amplitude of slightly dampened oscillator decreases by 3%. So in this case, the change here is 3% less, okay? And the question is, what percentage of the mechanical energy of the oscillator is lost with each cycle? So if this amplitude is decreased by 3% at each point, how much effect does that have on the energy? Well, we remember that the potential energy here is equal to 1/2 kx squared. So potential energy 1 over potential energy 2 is going to equal to 1/2 kx squared 1 over k 1/2 kx squared 2. And what we're saying is that the x is decreased by 3% with each move. So the ratio of the energy is going to equal the square of the ratio of the amplitudes. And if you decrease this by 3%, the square of 3 is 9%. So the energy is going to be dampened by 9% with each wave. Well, the answer is 9%.